Welcome back everyone. In this lecture we will continue with the character theory. We will first see some basic properties of characters. So, let us begin. So, let us recall the definition of the character. So, let us fix a representation of G, let us call it rho. So, we are assuming that G is a finite group and V is finite dimensional vector space over complex numbers. So, now what is character? So, character, it is a function from G to complex numbers where this character actually records all the traces of the actions of elements of G. So, given G, you take the trace of the rho of G, and so basically chi rho of G is given by this trace, and this is how this function is defined for all elements of G, and this chi rho is called character. So, this is the character of this representation rho. So, ultimately we want to prove that character completely determines the representation up to equivalence. So, for that we need to actually understand some properties of the characters. So, let us start with some basic properties. The very first basic property, you can see that the value of E under the character map is going to be the degree of the representation. So, let us write it. So, the character value of the identity element is exactly the dimension of V, which is same as the degree of the representation. So, how one can see this? So, recall that rho is nothing but group homomorphism from G to GLV. So, in particularly rho of the identity is going to be identity operator on V. So, in particularly the trace of this rho of identity is going to be trace of this identity operator, which is exactly the dimension of V, but that is the value of the character value of this identity element here. So, this actually proves that character value at identity should be always the degree of the representation. So, now let us ask this question. So, I said that the characters actually determine the representations up to isomorphisms. So, that means the map that we are defining. So, let us take our space, the representation space, this consisting of all, let us say 5 dimensional representations of G. From here, so we are actually defining a map which is the character map. If you think about it, that is actually complex valued function from G. So, where rho is mapped to chi rho. So, this is the map that we are interested in understanding. So, our first observation is that this chi rho is unique up to equivalence of representations. So, let me just state it here. Suppose rho is equivalent to phi. So, that means the representations are isomorphic. So, then we must have chi rho equal to chi phi. So, again this proof relies on the fact that trace function is well behaved. So, recall that the trace of AB is same as trace of BA. So, we just use this observation about trace function in order to prove this result. So, let us recall what is the meaning of equivalence of representations. So, let us say V comma rho is the representation, or V is the representation space for rho, and similarly W is representation space for phi. So, equivalence of representation means there exists an isomorphism, let us call it T from V to W, such that it commutes with the action of G. So, what does it mean in terms of the maps? Let us write it down. So, this T is a map from V to W. Now, we have this action. So, let us write down the diagram. So, we have V to W and then V to V, we have this action of G given by rho G, and then W to W we have the action of G given by phi G, and then we have this T. Now, we can actually reach here in two ways. So, this rho G composition with T composed with rho G. So, that is this way. So, that should be same as T composed with phi G. So, phi G composed with T, and this is true for all G and G. So, that is the meaning of homomorphism between V to W. Since T is an isomorphism as representations, so we must have this equality. So, now using this equality, since rho G, phi G all are invertible map. So, this can be rewritten as follows. So, T rho G T inverse, again T is also invertible map. So, that is same as phi G. So, that means if we take the trace of phi G, so this is going to be equal to the trace of T rho G T inverse. So, which is going to be equal to trace of, so using the property of the trace. So, we can actually switch these two. So, then we get exactly T inverse T rho G. So, that is going to give us trace rho G. So, that means, so this is the character value of phi. So, this is chi phi of G. On the other hand, we have chi rho of G. So, from this we conclude that chi rho is same as chi phi. So, I will actually make a remark. Indeed, we prove that in couple of lectures, that whenever chi rho is same as chi phi, then that would imply immediately that this rho is equivalent to phi. So, basically the characters determined by the representations up to equivalence of representations. So, this is something we will prove in the future. So, we will prove later. So, this actually, this observation indeed tells us the importance of the characters. Indeed, if we want to know anything about the representation, so it is enough to actually compute the character, and then the character will tell us everything about the representation. For example, we already know using the complete reducibility that given any finite dimensional representation can be written as a direct sum of irreducible representations. So, now if we actually want to know how the given representation actually decomposes into irreducible factors, then what we can do, we can apply character and then compute the character and then write the character in terms of the irreducible characters. So, that will actually tell us how to decompose given representation. Okay. For that purpose, we need to understand how the character behaves when we take the direct sum. So, this character function rho goes to chi rho, this is indeed very nice function. So, it is going to respect whatever operations that we have in this space of representations. So, indeed our proof tells us that so this map that we have from the representation space to this C valued functions from the group G. So, this actually satisfies this following property. So, if we take the equivalence class of representation, that is equivalence class is given by this up to equivalence relation. So, that is up to isomorphism relation. So, then we can easily see that this entire class is going to have same actually character. So, that is what we have observed. So, what we can do, we can actually go modulo this tilde. This tilde is given by isomorphism of representations. So, what basically I have written here, if we have representations which are isomorphic, then they will have same character. So, using this, now like we will have some operations in this space, the representation space. Maybe later actually I am going to explain more about what are all the structures like algebraic operations that we can perform on this representation space. At least for now, for time being, we know that already direct sum makes sense here in this representation space. So, now we want to actually understand how the direct sum indeed behaves. So, let us actually write down. So, if we take V and W to be two representations as before. So, maybe let me use V comma rho and W comma phi. So, these are let us say given representations, again all of them are finite dimensional representations of G. So, then if we compute the character of this direct sum rho direct sum phi. So, this is going to be exactly equal to the sum of the characters chi rho plus chi phi. So, recall that this space on the right side, this CG, this is indeed an associative algebra over C. So, that means we can be able to actually perform addition, multiplication and so on. So, that means we expect similar operations here on the left side. So, I will explain later like what are all those operations. But now you can see that at least addition is given in terms of the direct sums. Okay. So, the proof actually given as follows. So, recall how the direct sum is defined. So, the direct sum of rho and phi. So, this is a map from again G to GL of V direct sum W, where the map rho direct sum phi of G is given by. So, let us write it in the matrix notation. So, this is as linear maps, it is going to be direct sum of these two maps rho of G direct sum phi of G. But in terms of the basis, so if I take B1 to be basis of V and then B2 to be basis of W. So, then this rho direct sum phi of G, the matrix of this with respect to B, where B again basis of this V direct sum W obtained by putting together B1 and B2. So, that is going to be the block diagonal matrix. So, where first block is going to be rho G with respect to B1 and then 0 0 and then phi G with respect to B2. So, that means if we compute the trace, then what happens? The trace of this rho direct sum phi of G. So, this is going to be equal to the sum of the traces of these blocks. So, that means this is exactly equal to the trace of rho G plus the trace of phi G. So, that means the character value of this rho direct sum phi on G is going to be chi rho of G plus chi phi of G. So, this proves that the function corresponds to the direct sum is nothing but sum of this respective function. So, this is an important observation. So, later we will see that the multiplication that we have in this associative algebra, which is given by the convolution product, indeed corresponds to tensor product. So, I do not assume you know that tensor products. So, probably later in the later part of the course. So, I will actually define what is tensor product and then how to construct tensor product of representations and so on. Okay. So, now here is another important property of this character. So, if we actually look at the value of this any element g and its conjugate. So, they are going to be same under this character function. So, chi rho of g is going to be exactly equal to chi rho of h g h inverse for all g and h in g. So, complex valued functions from G satisfying this property, they are called class functions. So, basically we are saying that chi rho is a class function. So, this is indeed a class function. Okay. So, again the proof just uses the property of trace. So, let us recall. So, on the left hand side, this chi rho of g by definition is nothing but trace of rho g, and which is exactly equal to the trace of rho of h g h inverse, because recall that rho being group homomorphism, rho of h g h inverse is going to be equal to rho of h times rho of g times rho of h inverse, which is exactly rho of h inverse. So, that means the trace of the right hand side, which is going to be equal to rho of h, rho of g, rho of h inverse, and now using the property that this is, you can call it A and then this is B, then this is same as trace B A, that gives us that trace of rho of h inverse, rho of h, rho of g, and again using the property of a representation, you can actually combine this. So, this rho of h inverse, rho of h is going to be rho of identity, which is exactly the identity on V. So, that means this is going to be exactly equal to trace of rho g. So, that is what we wanted to prove. So, that means this character indeed is a class function. So, what is a class function? So, class function that actually takes constant value on the conjugacy classes. So, let us quickly recall what is a conjugacy class and so on. So, we have this group. So, now on this group we can actually define the conjugacy relation. So, let us call this tilde C is the conjugacy relation. So, what is it? So, we say that G1 and G2 from G, they are related by this conjugacy class conjugacy relation, that is G1 related to G2 if there exists H in G such that, so basically G1 is conjugate of G2. So, G1 given by H G2 H inverse. Now, it is not hard to prove that this is indeed an equivalence relation. So, that means the equivalence classes, so that is given by let us say the class G. So, it is not hard to prove, maybe you take it as exercise, that class G is going to be just all possible conjugates of G, and G is given by the disjoint union of these conjugacy classes. So, G is can be written as disjoint union of the conjugacy classes of G. So, let us denote this C L of G by the set of all conjugacy classes, the set of all conjugacy classes of G. So, then it is immediate that for any C and C dash from this conjugacy class, either we have C equal to C dash or C intersection C dash is empty. And not only that, G can be written as disjoint union of C, where C comes from this C L of G. So, now given this, we can actually define the space of class functions. So, recall this C G is nothing but the set of all C valued functions from G to C. So, basically this is set of all C valued functions from G. So, now we are going to define this subset, which is the set of all class functions. So, this is the set of all class functions. So, what is a class function? So, f in C G is called a class function if it satisfies the property that we mentioned before. That means, f of G is same as f of H G H inverse for all G H in G. So, that means, f is constant on given conjugacy class. So, that is f of G equal to f of G dash for all G comma G dash in C and for all C in CL of G. So, now what one can prove that the space of class functions, so that is indeed a subspace of C G. So, here is the proportion, the space of this class functions, this is indeed a subspace of C G, and not only that, of dimension exactly the cardinality of this the set of all conjugacy classes of G. So, which is called the class number. So, the dimension of C G is exactly the cardinality of C L of G, which we denoted by small c g, the number of conjugacy classes, the number of conjugacy classes. Okay, so why this is indeed a subspace? So, that is something easy to check. So, let us check this. So, to check it is indeed a subspace, let us take two elements from this subset, and then we need to prove that the linear combination of those two elements belongs to this subset itself. So, let us take C1 and C2 from complex numbers. Now, consider this linear combination C1 F1 plus C2 F2. So, we need to verify the property of class function. So, for that let us compute what happens to this conjugate of G. So, for G H in G, so let us compute this. So, this is going to be exactly equal to C1 of F1 of H G H inverse plus C2 of F2 of H G H inverse. But since both F1 and F2 are class functions, so this value is equal to F1 of G, and similarly this value is equal to F2 of G. So, then using this you can see that this is exactly equal to C1 F1 plus C2 F2 of G. And since this is indeed true for any G and H, so that means the linear combination of class function is indeed class function. So, that proves that this linear combination is inside your subset that we defined, and this is indeed a subspace. And that immediately implies that the dimension of this subspace is going to be at most the cardinality of G, but we want to claim that the dimension is exactly the number of conjugacy classes of G. So, for that what we are going to do, we are going to establish very explicit basis. So, recall that we had such basis, some basis for this the space C G. So, we are going to imitate that basis to get basis for this Z of C G. So, for C G, if you recall, we defined this delta functions. For given x in G, you define this delta x, which actually sees only the x. So, whenever x equal to y, then you get 1, otherwise you get 0. And we prove that these functions delta x, x in G, so they form a basis. So, they form a basis for this C G. So, that actually motivates us to define something very similar to these delta functions. So, even here in this setting Z C G, we will do the same thing. So, since class function actually takes constant value on the conjugacy classes, so what we do, we just define this delta function for the conjugacy class. So, for C in this CL of G, so we just define this delta C. So, this is going to be a function that is going to only see this conjugacy class. So, that means it is going to be 1 if this G is an element of C and 0 otherwise. So, now our claim is this collection of this delta C, where C is in CL of G. So, this is going to be a basis. So, this is a basis for our space Z of C G. Okay. So, how one can verify this? So, we just first to prove that any function f that is going to be linear combination of this delta C. So, let us start with the function f from this C G. Since it is a class function, so that means it satisfies the property that f of g equal to f of g dash for all g comma g dash from C for any C in CL of G. So, because of this, we can see that this f actually induces a function f bar from this the set of conjugacy classes to complex numbers. So, where f bar of C is defined to be, you just choose one representative from the conjugacy class and then take the value f of g. So, you just choose one g from C and then define this f bar of C to be f of g. So, now it is immediate that this f is as a function is going to be sum of f bar of C delta C, where C runs over CL of G. So, this indeed actually proves f can be written as linear combination of delta C. So, it is actually a quick check, I will leave it to you to check. So, now what we are going to do, so we want to prove that it is indeed a basis. To prove it is indeed a basis, we straight away prove that it is indeed orthogonal set. So, this B, which is the function delta C, C comes from the CL of G, this is indeed an orthogonal subset of C G. So, once we prove this, then it is immediate that this will form a linearly independent subset. Now, since it spans this Z of C G, so that would imply immediately that this is indeed a basis. So, how do we prove this? So, for this let us recall we have this following inner product on CG. So, given F1 and F2 from this CG. So, you define this inner product F1 F2 is given by this summation F1 of G F2 of G bar, where G runs over G with this average. So, now we can easily compute what happens to the inner product delta C and delta C dash. So, you can easily check, I will leave it as exercise, it is not very hard, that when you compute this inner product delta C and delta C dash, then we get exactly equal to, so mod C divided by mod G if C equal to C dash, 0 otherwise. That means C intersection C dash is empty. So, now this actually tells you that the set delta C where C runs over this CL of G, this is indeed orthogonal set. So, that would imply that this is indeed linearly independent. So, that proves that this set B delta C C in CL of G, this is a basis for this class set of class functions. So, as an immediate corollary, we get that the dimension of this space is exactly the number of conjugacy classes. So, that actually completes the proof. Okay, so, I will stop here and then we will continue with more properties of characters in the next class. Thank you.